Say a line is an exterior line if it does not pass through any part of the circle. You have a little picture to the bottom right of these 4 words. Label which line represents an exterior line. One of those 4 does not pass through any part of the circle. A line would be a tangent line if it passes through precisely 1 point. That's what we learned yesterday. A tangent line intersects a circle at exactly 1 point, so label your tangent line in your picture. Here's our new word for the day, a secant. One of them. A secant line is a line that passes through 2 points on the circle. And then the last phrase says that a line cannot pass through any more than 2 points on a circle. If I have a circle, there's no way to draw a line that's going to pass through more than 2 points. You can only pass through 2. 1, 2, or 0. Got it? Okay. So your exterior line, you should have had that labeled at the top. Then comes your tangent line. It's intersecting at 1 point. Then this is your secant line, the third one. It intersects it at 2 points. And then the third one they call the secant through the center. Still a secant line, it's just passing through the center of the circle. Alyssa, what would you call this part of the secant line? Good. This part of a secant line right here, in purple, that's called a chord. A chord is a segment whose endpoints are on the circle. So, Alyssa, would you consider the diameter to be a chord? Yeah. Yep. The diameter is a chord because its endpoints are on the circle. That's what the next definition is. A chord. There you go. Is a segment who has endpoints on the circle. So I'd call that chord PQ. Here's your first theorem. There's 3 parts to it. Within a circle or among congruent circles, congruent central angles have congruent chords. Central angles. We talked about this in chapter 10, 2 chapters ago, when we found like area of sectors and arc lengths. A central angle is formed by 2 radii, and then its vertex is on the center, so there's a central angle. Draw a couple more in here. So let's pretend that this one is congruent to this one. If those 2 central angles are congruent, then their chords are congruent. And the chord is a segment whose endpoints are on the circle. So if these 2 central angles are congruent, then the chords that correspond with them are congruent. This length would be the same as this length. Congruent chords will have congruent arcs. That's like the pizza crust. This blue arc then is going to be the same length as that blue arc. And then if you have congruent arcs, the blue things, then your central angles must be congruent. So you kind of have like a recyclable Venn diagram thing, spiderweb thing off to the right. It's a cycle. Congruent central angles mean congruent chords, mean congruent arcs, means congruent central angles. Okay, so if I didn't even mark the angles congruent, but I marked the chords congruent, then you should know that the central angles have to be the same. Got it? Cool. This one's not on your notes. In the diagram, segment OX bisects angle AOB. Gracie, what's it mean to bisect an angle? Good. So then angle AOX is going to be congruent to angle BOX. Raise your hand if you can conclude anything else from that slide. Melissa. Why are OA and OB the same length? What's the theorem say? Okay. What does OA represent on my picture? What kind of line? Yup. Yep, so why is OA congruent to OB? There you go. Those two are congruent because they're both radii in the same circle. Zach, you got something else? Why is arc AX congruent to arc XB?
Congruent chords have congruent arcs.
Okay. What chords are congruent then? Is OX a chord? Okay, so which ones are your congruent chords? Good. Segment AX would be congruent to segment BX. Those are your chords. And when you have congruent chords, then you have your congruent arcs. Zach, what is OX? How would you describe that in relation to the circle? That's okay. Yeah, but what would you call it? That's a radius. There you go. So it'd be congruent to Alyssa's that she named off, right? Okay. So congruent chord, congruent central angle, congruent arcs. Next theorem. Within one circle or among congruent circles, chords that are equidistant from the center are congruent to each other. What's equidistance mean? Exactly, equal distance, the same distance away. This is circle X. Name it by the center of the circle. We'll call this chord EC. And we'll call this chord JV. And EC is going to be 4 units away from the center of my circle. And JV is going to be 4 units away from the center of my circle. What can you conclude about EC and JV then? That they're congruent. Since they're the same distance away from the center, then the chords must be equal. EC must be congruent to JV. The second part says that congruent chords are equidistant from the center. Ooh, that's a big circle. Here's circle P. Here's chord CH. Here's chord MF. CH is 16 and MF is 16. Since they're the same length, the distance from P to MF is going to be the same as P to CH. Those little segments in there are going to be the same length then. Congruent chords are the same distance from the center. If chords are the same distance from the center, then they are congruent. These are all going to be converses of each other. If it works one way, it's got to work the other way then. Got it, Spence? Okay. Do the next two on your own. Last rules for the day at the bottom, then we're going to apply them all. In a circle, a diameter that is perpendicular to a chord bisects the chord and its arc. So that rule looks like this. You have a circle, we'll call it circle X, and chord EP. And here's the diameter. If the diameter is perpendicular to the chord, so if it looks like that, then you can assume that EC is congruent to CP. It's going to bisect the chord, and it'll bisect that arc. So, I don't know, EM would be the same length as MP then. So if the diameter is perpendicular, then the chord's getting bisected, and its arc. Rule 2. In a circle, a diameter that bisects a chord is going to be perpendicular to the chord. So rule number 2 or 12 point 7, I guess. Circle Q, chord WC. Here's my diameter. If your picture looks like this, or the diameter is bisecting the chord, then you can assume that it's perpendicular. Again, they just go backwards. If a chord is perpendicular to a segment, then it's getting bisected. If the chord is getting bisected, then I know that it's perpendicular. Then the third one, in a circle, the perpendicular bisector of a chord contains the center of the circle. All right. There's chord MS. If this vertical line is perpendicular and bisects the chord, then it must be passing through the center of our circle. It has to be the diameter or a radius. If a chord is getting bisected and is perpendicular, then the guy that's doing the cutting in half must be coming from the center of the circle. I mean, think about that, you guys. If I have a circle with a segment going through it, and I want to cut that in half, I mean, it's not going to make sense to cut it in half over here, is it? No, it wouldn't make sense to cut it in half over here. If it's going to go straight through the chord, wouldn't it have to go straight through the center of the circle? Right? Okay. Here we go. We're going to put them all into play now, so go ahead and flip it over. It says that P and Q are points on circle O. So then PQ, that's going to be a chord. The distance from O to PQ is 15 inches, and the length of PQ is 16 inches. We have to find the length of the radius. Remember, the distance between 2 points or 2 objects is also like the length of the line connecting them. So when it says the distance from O to PQ, well, the line that connects O to PQ is this guy, so that little box over here is where you would put 15 inches. And then the length of PQ is going to be 16 inches. We have to find the radius. Since my chord is is perpendicular, then what do I know about PM and MQ? Yeah, they're getting intersected, but how? Do I know that? So then they're intersected at the what? Like, is it? What? Yes, the center of the line. So what would I know about PM and MQ? They're congruent. Good. It's going to get bisected. If a chord shows a right angle, then it's getting bisected by the segment. So Trevor, what would be the length of PM then? And we know that MQ is 15. So Megan, what are we going to use to find R? Good, your Pythagorean theorem. 8 squared plus 15 squared equals R squared. It's a weird 7. You should get a radius of 17 inches then. Go ahead and do the next one. Lens, did you get the second one on the back side? I'll give you a second. Yeah? Okay, tell me what you did. Good. Excellent. Go ahead and do the third one. What'd you do?
11 squared equals 15 squared. Yeah, 121 plus b squared equals 225.
Okay.
And I subtracted 121 from 225. And then got 104 and then squared it.
How'd you know you could use the Pythagorean theorem?
Because it's like the center angle, like how it's perpendicular or something like that, or at the center line. I don't know.
How'd you know it's perpendicular?
But that's one of the theorems.
What's the theorem say?
Diameter that is perpendicular. Yeah, diameter that is perpendicular. No. I don't know.
Find it. What theorem tells you that you know you have a right angle there?
Perpendicular bisector.
No.
The diameter that bisects a chord is perpendicular to the chord.
Yes, I'll take that one. Because you know that the chord was getting bisected, 11, 11, then you know that you have a right angle there. So if it gets bisected, then it's a right angle. If it's a right angle, then it gets bisected. Got it, Gracie? Yep. Okay, do the last one. And you should get 11 as your answer.